Okay, these two last talks have been very inspiring. It was great fun. Now, the current talk that I will present will not be about applications. It will have very real-world situations. Another difference is that it will not be funny, differently from the other two talks. So I'll talk about, but the good news perhaps is that according to the theory that I'm going to present, even though this talk will not be funny, I will benefit from the two talks that were before me, and you will nevertheless be attentive. So I'm going to explain this further on. I'm going to discuss attention as the missing dimension in decision research, the example of losses, and it's joined with a couple of persons that you see here. And I'm also thankful for the insightful guidance of Danny. Danny had been my PhD advisor. He inspired me to think about this attention model that I will present to you today. And he also had some specific contribution, which I will show you. So I will talk about losses. This is the topic of my talk. At the heart of many theories in behavioral science is the assertion of loss aversion. And what is loss aversion? When you ask lay people, what do you believe in loss aversion, Sinat said? So of course we believe in loss aversion. We don't like losses. Yeah. Of course loss aversion is true, because we all avoid losses, right? That's the reasonable thing to do. But in psychology and economics, loss aversion is not the fact that you avoid losses. It's a stronger argument that the weight of losses is larger than the weight of gains of the same value. So you can think about it metaphorically as a tilted scales. Say you have two materials, material A, material B. They both objectively weigh 1 pound or kilo, but when you put them on the scale tilts towards material B. It comes out as being heavier. And why? Because the materials are gains and losses, and the scale is that of subjective impression. And the impression we get from losses of the same weight as gain is heavier. They loom larger, in Kahneman and Tversky's word. And this has been the basis of theories such as mental accounting theory, particularly the endowment effect, the fact that people give more price for selling things than for buying things. And the idea is that when you sell things, it's like a loss, and you have to be compensated for that to a greater extent. It's also the basis of inequality aversion, a very influential paper by Fer and Schmidt, and also used in connectionist modeling. But there could also be other intuitions. For example, Elizabeth Bishop, in one of my favorite poems, in the movie in Hebrew, Benalea, says, the art of losing isn't hard to master. So many things seem filled with the intent to be lost that the loss is no disaster. So Elizabeth Bishop suggests that losses, if not disaster, if they're not disastrous losses, they are not disasters. That is, we all have losses from time to time, and we get used to the fact that life is full of losses. So who is right? In the literature, it's been argued that indeed there's a profound asymmetry in the effect of losses and gains on human behavior, and indeed this has been pretty much established in riskless decisions, that is, in the effect of losses and gains on performance. For example, in an early study, Constantini and Hoving used the task of walk slowly. There is a beam on the floor, and your task is to walk as slowly as possible, and you get points for walking slowly. Now this seems like a very easy task, but for children it's very difficult. Children like to go fast, and it's very difficult for them to go slowly. And in this study they had two conditions. In one condition, children got stars for their performance. The more they succeeded, the more stars they got. In the other condition, the loss condition, initially they gave them a whole bunch of stars, and they took stars away from them for performing poorly. So one condition was gaining stars, and the other was losing stars. The loss condition led to much higher performance. So there's a clear asymmetry. This has been replicated many times in adults as well, although not in this task, that losses have a larger effect on performance than gains. Now the same effect has been hypothesized in decisions under risk. And how is it operationalized in decision under risk? Very famously, Kahneman and Tversky asserted that most people would find symmetric bets of the form 0.50 to win or lose X distinctly unattractive. What does this mean? It means that if you have a gamble where you have 50% to win something, say $10, and 50% to lose the same thing, say minus $10, you would not like this gamble. Why? because you are more affected by the loss component than by the gain component. Therefore, this gamble doesn't seem equal. Although it is objectively equal, it would not seem subjectively equal. That's why you would avoid such gambles. Interestingly, in the famous paper, 79 paper that was the basis of the Nobel Award that was given to Kahneman, they never showed that empirically. It was only a hypothetical example, unlike some of the other effects they demonstrated. We ran some replications of this. Initially, we wanted to study whether this effect is also observed in decisions from experience, which is a paradigm that Ido devised, Ido Erez, and we didn't find it. And let me show you one of the experiments. We didn't find loss aversion. This is one of the experiments that we ran. In this paradigm, you don't have easy descriptions of probabilities and outcomes. You have buttons. And you learn from your experience. You press a button, you get some outcome. You press a button, you get some outcome. You do that many times. And the outcomes from the buttons are drawn from a gamble in the following manner. In this particular study, we had two problems. One problem we call the mixed problem because it has both gains and losses. In this problem, one alternative gives you 0 for certainty. That is, each time you press a button, you get 0, 0, 0, 0, 0, 0, 0, 0. In the other alternative, you get plus or minus 1,000 with 50%. Plus 1,000, it's random, randomly drawn from this distribution. So what would loss aversion predict? Obviously that you would avoid the risky alternative because this is an exact example of a symmetric gain and losses. Because losses loom larger, you would not like this risky alternative. Then we had another problem where we didn't have losses. It was in the gain domain. We just added a constant of 1,000 to everything so that no losses were possible. Now, loss aversion also predicts that the risky alternative would be less attractive with losses, that you would like the risky alternative less in this problem where it also includes losses. And here's what we got. In the mixed condition, we didn't get loss aversion. People like this alternative similarly. The proportion of risky selection were 52%. They didn't behave as if they were loss averse. Now in the gain condition, interestingly, they liked the risky alternative even less. That is, paradoxically, they liked the risky alternative more when it included losses than when it didn't include losses, which is completely opposite to the idea of loss aversion. So what's happening here? Now, there's some trivial explanation to the difference between tasks. If you believe in a Bernoulli utility function, it's not that if a payoff is raised, is multiplied by 2, that you liked it twice. If you like it a little less, as if you raise everything to the power of alpha, and alpha between 0 and 1, then this 2,000 is discounted to some extent, and this could explain the difference between tasks. But it could not explain what is happening here. Why do people still continue to take risk when risk involves losses? Now, in a review of the literature I did with my past student, Guy Hochman, we found that actually many people have found this before us. We were not the first to find it, but people didn't make a big deal out of it, that there's actually no loss aversion. For example, these were studies of experience-based decisions, and the N is for no loss aversion, and Y is for yes loss aversion. All of these studies in decision from experience, similar to what we did, didn't find loss aversion. Actually, in decision from description as well, where you actually present, what is decision from description? You actually present a gamble. You choose between 0, probability of 50% to gain or lose something. They also didn't, most of these studies, they also didn't find loss of it. They didn't find that people avoid this risky alternative. But actually, I'm cheating a little bit, because there are studies that did find it. But the studies that found it didn't use a fair paradigm of comparing two alternatives. They used a paradigm known as accept-reject. Now, if I were to tell you, would you accept a gamble where you have 50% to win or lose $20? Most of you, I would bet, because I did this experiment many times, would say no. And this is what happened in this experiment. When you tell people, would you accept a gamble where 50% to win, or people say no. But it's not fair. It's not fair for two reasons. Why? First of all, there's a status quo. Once the if we believe in the status quo effect, that is that you stay with what you have is you don't have the gamble. In this case, rejecting the gamble is also staying with what you have. So the status quo and loss aversion works in the same direction. So people don't take the gamble simply because they don't like to change. And indeed, if I were to present you the same gamble without losses, that is, would you take a gamble? I'm telling you, now have $20, right? I'll give you, imagine. You now have a choice whether to accept a gamble where you get 0 or $40. Most people would not accept this as well. So it's not the losses. It's simply that people don't like to get into risk. It doesn't have to do with losses. So this was kind of the first questions, or strong questions that we have about the existence of loss aversion. Now another area where loss aversion has been reported is not in behavior, but in brain activation. Many studies have found that specifically autonomic activation and also frontal activation, cortical activation is higher following losses compared to equivalent gain. And we wanted to see whether we can find the same things together, that is, no behavioral loss aversion, but more activation, more brain activation following losses compared to equivalent gain. Our initial studies focused on pupil diameter as a measure of arousal. In the study with Guy Hochman, we had, again, the two-button paradigm, two problems. In one, you have a safe alternative producing 1 or minus 1, 50%, a risky alternative 2 or minus 2, and then we had the gain condition where we just had a constant of 3, so no losses were possible. First, we looked at the behavioral choices. Again, we find no loss aversion. People pick them about equally. Now, in this experiment, we also attached the participant to an eye tracker, so we could examine their pupil diameter. Pupil diameter is a very sensitive, actually made famous by Kahneman, measure of autonomic arousal. And it's controlled by both the sympathetic and parasympathetic branches of the autonomic system. And you know why when we are stressed, the pupils get wider, they dilate. Why? Because in poor lighting condition, when our pupils dilate, we see more light enters the eye. So this is good if you are in trouble, that you see a little bit more clearly. And this is our pupil diameter result. What you can see, on the y-axis is the side of the pupil. On the x-axis is time. And the dotted line is losses. The non-dotted line is gains. So you could see that about half a second to a second after the losses, the pupil get a little bit larger compared to gains. And this only happens for absolute losses and not for relative losses. It doesn't happen for 2 compared to 4 or 1 compared to 5, but only minus something compared to plus something. But this is simultaneously with no loss aversion. So behaviorally, people don't behave as if they give greater weight to losses than to gain. But in their brain, people are activated more compared to in losses compared to gain. And we also replicated that in a host of other autonomic measures. Here's an example of heart rate. The heart gets faster after losses compared to gains. This is absolute losses compared to absolute gains. This is relative losses. And also in this little thimble that Perez showed you in the beginning of the day, peripheral arterial tone also gets higher following losses compared to gain. Again, everything is simultaneously with no loss aversion. So we have some kind of puzzle here. But before I get to the puzzle, I want to show you another classic result by Gehring and Willoughby. This is considered a pioneering brain study which found an effect also related to losses called the feedback-based error-related negativity. They had a task similar to ours. This was published in Science, I believe. You have to press one of two buttons. In one, you see the number 25. In the other, you see 5. If you press 25, there's 50% that you win 25, 50% that you lose 25. If you press the 5, the 50% that you win 5, 50% that you lose 5. And you know that after you chose. And they studied EEG and ERPs, and what they found is that after losses compared to gain, about 250 milliseconds after the stimulus, there is increased activation all over the frontal cortex. The frontal cortex burns when you get losses compared to gains, and it's located at the frontal lobe in or near the anterior cingulate cortex, which, by the way, also produces sympathetic arousal. And Gehring and Willoughby's explanation for this was that here is a brain activation pattern that's consistent with loss aversion, and they suggested that it actually drives loss aversion, that you have an asymmetry in the weighting of losses and gains in the frontal cortex, and these affect the later behavioral sensitivity, that we are more sensitive to losses compared to gain. But there is one problem with this explanation. Even in this experiment, actually participants didn't avoid losses. They actually picked the risky alternative with the higher losses 58% of the time. So the brain behaved as if it's activated more after losses, but in their behavior, they didn't behave as if large losses was something that they had to run away from. So we have kind of this puzzle where, on the one hand, losses increase performance. On the other hand, there is no behavioral loss aversion in decisions under risk and uncertainty, and losses increase arousal even with no loss aversion. So at this point, I had two possible models for this. One was that what losses do is they inflate, but not only the loss component, but rather all of the payoff. They do some kind of, they make the thing more important, So everything is inflated. Everything is more important in your mind. The other explanation, which is a cousin of the first explanation, had to do with attention. And the idea is that when you choose between two alternatives, you don't only choose between alternatives, there's another choice. And your choice is how much attention to invest to these tasks as compared to other things in the world. And the idea is that if you have losses, you invest more attention in the task. And what does this lead to? It leads to more performance because you have more attention, more performance until a certain level of attention. Then it doesn't affect risk-taking, but it does affect arousal because increased arousal is the hallmark of an increase in attention. And at this point, I submitted a paper, and I got kind of a weird review, and I didn't know which models to pick. And I consulted with Danny, and I sat with Danny for about an hour and a half, and I debated with him about what to do. Which one of these two, which road should I take? Should I take the losses inflate or subjective payoffs, or should I take the attention approach? And Danny said, go for the attention.
What should I say?
Go for the attention. And that's what I did. And now I think that in part, Danny's suggestion is based on his own theory. And you know, one of Danny's most cited paper, at least the last time I checked, is this paper with Navon, a psych review, which was mentioned previously. And I think Danny had two contributions with this paper. One is that he offered a very elegant quantitative approach to the idea of attention allocation between tasks. The other thing, which is fantastic, is that they propose all kinds of these exceptions to what's known as the strict capacity, central capacity interference model. These models say one thing, but sometimes other things occur. And later people identified that these other things really occurred. And one of the things that they propose, it has to do with symbiosis between tasks. I will tell you what it is. The central capacity interference model says there's no symbiosis with these tasks. That is, when you put these two tasks together, there shouldn't be an interaction. And LNG say, although the possibility that a task benefits to some extent from being conjoined with another task appears to, at the first glance to be implausible, how can, when you put tasks together, it will be more easier, for example, to process the first task? It should be harder. But actually, there are cases where it is. For example, there may be some symbiotic relations, namely that the output or side effect of one process make processing of the other easier. Let me demonstrate to you this kind of symbiosis in losses. Here's an experiment with it. You have two types of trials in an experience-based task, again using the two-button paradigm. The first task doesn't have to do with losses. You have one alternative called L for low expected value, which produces 1 or 200 with equal chances. The other alternative produces 1 with probability 0.3 and 200 otherwise. That is, you should pick the alternative H to get more money, okay? In this task, there are two types of trial. One type of trial is like this. The other type of trial is a different task, where you get the same thing for both alternatives. You get X. In the gain condition, you get 5. In the loss condition, you lose 5. Now, according to these central bottleneck theories, these are two tasks. Joining them shouldn't have a beneficial effect. Could lead to some worsening of performance in the first task, but no beneficial effect. But according to the attention idea, if you have losses, you pay attention. If you pay attention to everything, including the first task. So you might be better on the first task. The trials, by the way, were randomly placed. Each time you selected in each trial, it was randomly decided whether it will be of type trial A or trial B. And these are the results we get. Actually, we get higher performance, 30% increase, 30% in advantageous selection, at least the beginning, in the condition with losses compared to the conditions with gain, so by adding these things together. And of course, this is not predicted by loss aversion, because loss aversion will not give you anything in this task, because in both alternatives, you get the same loss. Here's another example of why attention is important here. Here's another task that we ran. In this task, you have two alternatives again, starting in the gain condition. One produces 15 with some noise, and the other 17 with some noise. Your goal is to identify which one produces higher payoff, because you get money in the end, according to this payoff. And we had a loss version of this, where we just multiplied everything by -1, okay? Now, this is kind of an easy task, and indeed, where we just have these two buttons together, we give people 4 seconds to respond. There is no significant difference, and actually they perform slightly better in the gain condition. This is a small sample of subjects, but there's no significant difference. Okay, so losses don't improve performance here. But what happens when the task is more resource demanding? Now we put the same task as a secondary task in a paradigm. So you have a primary task, which was a bit like the first. You have one alternative producing 150 or 0, and another 150.7% of the time or 0, so the age is better. And your secondary task is exactly what I showed you in the previous slide. And again, we have two conditions here. One, when the secondary task is positive, and one when the secondary task is negative. So would losses effect work here? And the answer is they do. They do. And here, when attention resources are few, losses come into play. And performance is 50% higher in the second task when the second task is a secondary task. What is the idea? What's happening is that in the last slide, you had a lot of time, 4 seconds. Your attention was fully invested to the task. It was easier to find. Some people know. Some people didn't find it. No, not everyone is sophisticated. But for those who pay some attention, it's easier to find what is the correct thing. But here it's difficult to pay some attention. And losses kind of direct your attention when the attention resources are slim. Okay. So I have very little, I have 3 more slides, that's it. Here's another example of why attention is important, why an attention model is more important or works better than simply a weight model. This is a study not by me, by Dennis Raj and Epstein. Epstein is one of the most insightful people, I think, in psychology, is one of the originators of the two-system theory that Danny, by the way, hates so much. But this is a very cute experiment. Imagine that you have 2 jars, and they're full of candies, beans. And they're full of red bean, but there's some white beans. And your goal is to pick out the white bean in the first condition. Now, in one jar, you know that there are 7 white beans out of 100. In the second jar, there is 1 white bean out of 10, right? And your goal is to pick out the white bean, right? Now, it's clearly, now in the gain condition, you win $1 if you get the red, right? So what is the correct answer here? What you should do? You should go for here, of course, right? 1 out of 10, better than 7 out of 100. But some people don't understand it. There are all kinds of biases that actually lead people to select this alternative. One of them is oversensitivity to numbers. You know, the 7 is larger than 1, the 100 is larger than 10. So some people go for the 7 out of, they made this mistake. In the loss condition, it's the same thing, but now you lose $1 if you do not get the red. Now, what happens is that people make a mistake 31% of the time in the gain condition and 19% of the time in the loss condition. So losses have this effect of reducing mistakes level. So this was the first experiment, again showing that losses have an effect on performance. Now, Dennis Raj and Epstein also had another experiment, which is less well known, and that is they played only with the gain. They had no losses, and they had 2 conditions. In one condition, you get 10 cents if you get the red. In the second condition, you get $5, this is a mistake, if you get the red, okay? 10 cents if to get the red, 5, so they multiplied the gain by 50 times, all right? And this actually had absolutely no effect on performance. So if we were to stay with the weight model, we would have to say that the effect of losses and gain is 50 times % multiplication. This doesn't make sense. How could a loss be multiplied 50 times? Something doesn't work here if you just stay with weights in the discussion. You have to move to a different dimension and talk about losses to understand that losses introduce something that gains do not. And that is, they just put you a little bit into the task. This gets you more attention. This gives you more performance. So, in summary, I think that the attention-based model provides sufficient condition for many of the extant effects of losses. I only presented you some of these effects. And more broadly, I think that the tilted scales paradigm, you shouldn't worry about that. It should be replaced to a paradigm where there's an attention sign. That is, that losses just draw your attention. And this, I think, has 2 kind of morals. One is that losses increase attention, increase performance. And the other thing is that losses are very often not only not a disaster, as Elizabeth Bishop suggested, but they also sometimes imply an opportunity. And why do losses get attention? So a tilted scales kind of explanation would say something like, hey, losses get attention because they're more harmful than gains. But how could it be when we are not loss averse? So an alternative explanation would say something like that. There are many situations in life where having losses also signal the availability of resources. Let me give you 2 examples. Danny Gopher sold me a jacket. It's a true story. And he told me that, imagine 2 conditions. And one, the true condition is that Danny told me this jacket, it's worth €100. So by buying the jacket, I'm losing 100 euro. All right? So I'm imagining, what is the worth of this jacket? Must be a cool jacket. Now imagine another condition. Then it sells me a jacket, I'll give you this for free. Now I'm like, what is this worth of the jacket that he's giving me for free? So I know that by having losses, there's something good here. The fact that Danny demands a loss implies that there is some resource that he should be compensated for losing. So losses in barter situation often imply that there's something, that there are also resources. Or think of another story. Imagine that you're walking in the desert, yeah? And you're thirsty. And you see some kind of plant, and the plant, doesn't have any thorns or anything. Yeah, so what's the chance that there's water in it? Very slim. Now you go in the desert, and there's a plant with huge thorns that cut you. They do losses. Now this is a cactus, and maybe, in cactuses, there's a lot of water. What I'm saying in this example is that in natural defense systems, very often, where you have losses, you also have resources. Also, another example is with elk. Very often, the elks that are the higher, that have the best meat, also have the largest horns. So the losses are a signal of resources. So I think I would end with that example. Thank you for your attention, and thank you, Danny.